So let's further talk about heat flow. There are two kinds of heat flow. There's the exothermic and there is the endothermic processes of heat flow. So let's take a look at a couple of examples. Let's say that you and your friends are around a campfire, okay? And if I identify the system as you, um, and the surrounding, actually, I'm actually going to go take that back. If I say the system is the fire and the surrounding is you, then the heat is flowing from the fire to you and your friends. And so this will be considered an exothermic process. However, if I define the system as you and the fire to be the surrounding, then the heat is flowing from the fire to you, and this will be considered an endothermic process. Let's take a second example of you sweating while playing sports. And let's consider, or let's define the system as first you, okay, and the surrounding will be the sweat. Then the heat is flowing from you to the sweat, and so that will be considered an exothermic process. However, if I am interested on the sweat itself, and I define the system as the drops of sweat, and I say the surrounding is you are surrounding the sweat, then the heat goes from you to the sweat, and so this will be considered an endothermic process. So it's very important what we identify as our system and what we identify as our surrounding. We talked about this also in class, in that heat capacity we're going to define as the amount of heat needed to raise the temperature of an object by exactly 1 degree Celsius. So the units, it seems that it's per every degree Celsius, and is the amount of energy per every degree Celsius. So it is the unit's going to be in joules per degree Celsius, or I will also take calories per degree Celsius. Specific heat capacity is specifically for 1 gram, so it is the amount of heat needed to increase the temperature of an object by exactly 1 degree, specifically for 1 gram. So, and this specific heat capacity is now going to get a symbol of C. So Q would be heat, T would be temperature, and C is now the specific heat capacity. And the units for this variable is going to be the amount of energy that is required for per every 1 gram per every per every degree Celsius per every 1 gram. So it could also be in calories per degree Celsius for every degree Celsius, and for every gram. So the grams and the degree Celsius are both in the denominator, and the calories or the joules are going to be in the numerator. Water has a huge specific heat capacity, meaning that it takes a large amount of energy to raise its temperature by 1 degree for every gram of it. So let's take a look at a chart that will show you all the specific heat capacities, or many specific heat capacities. Over here, is my liquid water. And liquid water has a specific heat capacity of 4.18 joules for every gram for every degree Kelvin in this case, which is the same thing as, because 1 Kelvin is equal to 1 Celsius, 1 degree Kelvin is equal to 1 degree Celsius. joules per gram K is the same thing as joules per gram degree Celsius. Okay? And you can see that the water has a specific heat capacity of 4.18 joules per gram Celsius, which means that it actually needs twice as much as energy to raise the temperature of liquid water than solid water, which is ice. And a gas is even easier to raise its temperature by 1 degree for every gram of water. Versus iron needs very little amount of energy for every gram of the iron to change its temperature by 1 degree. And this makes sense in that if you, on a hot day, if you have like a metal floor, and then you also have water next to it, if you were to step onto the metal floor, it's going to be hot. But if you step onto the water, it's going to be really cool, because water needs more energy to raise its temperature by 1 degree versus the metal needs a little bit of energy to change its temperature by 1 degree. So the metal is going to raise its temperature easier than the water would be able to. Going back to this, please remember these values over here. Water has a specific heat capacity of 4.18 joules, and ice, solid water, has a specific heat capacity of 2.06 joules per every gram degree Celsius, and gaseous water, which is steam, has a specific heat capacity of 1.87 joules per every gram Celsius. All of this down here, you do not have to memorize. However, these three up here, you do have to memorize. So please note this in your journals and make sure it is available to you. So I told you in this chart that liquid water has a specific heat capacity of 4.18 joules per gram Celsius. This 4.18 joules is a familiar number to us in that 4.18 joules actually equals 1 little c calorie. And so considering that specific heat capacity of water is 4.18 joules for every gram of the water to change its temperature by 1 degree, if I were to have the specific heat capacity of water in calories, then it would be 1 calorie for every gram of water to change its temperature by 1 degree. So specific heat of water can be expressed in both ways. And because water has a high specific heat capacity, it takes a long time to heat up. And so water does take forever to boil, or to go from room temperature to boiling point. So this is the very first example that I'm going to show you. This is going to be the very first of 3. So let's find out how to do this calculation, and you guys are going to have no problem with this. It says the temperature of a 95.4 gram piece of copper increases from temperature of 25 degrees Celsius to 48 degrees Celsius when the copper absorbs 849 joules of heat. What is the specific heat of the copper? So let's actually start out, before we do the specific heat capacity, let's do heat capacity. And you know that the heat capacity is the amount of energy that it requires for every degree Celsius change. And so this is the amount of energy. 849 joules is the amount of energy that was inputted to the copper. And for it to change by 1 degree, to know how much energy was required for every 1 degree change, I would have to divide this number by 23 to find out how much energy was absorbed for every degree change. And I actually messed up because this is supposed to be 23.0 degrees Celsius. And so that gives me 3 sig figs, and it's supposed to be 36.8 joules for every degree change. But I want the specific heat capacity, meaning I want it for specifically for every 1 gram. So I have to divide this number by the mass being, I'm actually going to extend this, 95.4 grams, and that gets me 0.38, how many sig figs? 6 joules per gram degree Celsius. So this is my specific heat capacity. But let's actually see what I did in order to solve this problem. I took the energy and I divided this energy by the amount of mass I have, and I also divided this by the amount of temperature change there was, and I got the specific heat capacity, which now I'm going to symbolize in my letter C. And so if I were to rewrite this, I'm actually going to write specific heat capacity. Specific heat capacity. And if I were to rewrite this, I could write it as energy being expressed in Q divided by the mass expressed in the letter M, and the change in temperature, which is expressed in delta T, is equal to the specific heat capacity, which is equal to my C. And if I were to rewrite this in one line, I could say Q is equal to C times by the mass times by the delta T, which means that the amount of energy released or absorbed is equal to the specific heat capacity of that substance times by the mass of the substance times by the temperature change of the substance. And this becomes my formula that I am going to apply to all of my problems, or if not most. Remember that the specific heat capacity is different from the heat capacity, in that heat capacity is for every joules is the amount of energy per every gram, versus the specific heat capacity is the amount of joules for every gram to change its temperature by 1 degree. And the formula provided is Q equals Q, which is also expressed as delta H in this open system, constant pressure system, is you know that they're the same, is equal to the mass times by the specific heat capacity times by the temperature change. Remember that the Q and the delta H are going to be negative in an exothermic process because the heat is being released by the system, and it's going to be positive during endothermic system because the system is gaining the heat. So if I were to say, if something were to get hotter from 10 degrees Celsius to 30 degrees Celsius, your change in temperature, which is the final temperature minus the initial temperature, is plus 20 degrees Celsius. So, which is going to, if I do Q equals mass times by C times by delta T, remember this C is always positive, the mass is always positive, and in this case the delta T is positive, which is going to give you a positive Q, which is an endothermic process. The system has gained heat. However, if I say that something has gotten cooler from 75 degrees Celsius to 25 degrees Celsius, temperature change is again T final minus T initial, which is in this case negative 50 degrees Celsius. So if I do Q equals mass times by specific heat capacity times by delta T, this mass is always positive, specific heat capacity is always positive, because it is the amount of energy needed for 1 gram to change its temperature by 1 degree, or to increase its temperature by 1 degree. The delta T in this case is a negative value, which is going to get you a negative Q value, which is going to be an exothermic process. The system has lost heat.